Alrighty, so today we're going to talk about minerals. Minerals is something, again, depending on the class, we go into it in a varying degree of depth. In geology, of course, we've got a lot of minerals in lab that we work with, and big mineral tests. In some of my other classes are science, for example. We touch on minerals, the importance of minerals. They look at a few minerals in lab, but we don't hold them responsible for being able to recognize them. All right. But this lecture is pretty much the same regardless of which class you're in. For those of you listening to this lecture that are in my earth science class, when I make some references to lab here and there, again, keep in mind that for the most part it probably won't apply to you guys too much. So, reflecting back on, I guess it was the atomic review PowerPoint that we did a while back, the big question at the end was, why did you use my time to talk about this stuff? And I said, well, of course, we're studying the Earth, and the Earth is full of elements, whether you're looking at the atmosphere or the rocks itself. Those elements are in the form of minerals, and so on and so forth. And then, in order to understand minerals and elements, we need to understand protons and neutrons. So we're going back into that context now, and we're looking at sort of an intermediate here. Okay, we're not talking about protons and neutrons, and we're not quite talking about rocks or the Earth as a whole yet. We're just going to talk about those guys in the middle, minerals. So a mineral is something that's composed of one or more elements. Okay? This is not the definition. I am, at some point, going to hold you responsible for the definition of a mineral. All right? Yeah, well, actually, this test. Please don't write something that is composed of one or more elements. That is, again, not the definition. It's just a statement, really. It's like saying meatloaf is made of ground meat. Well, that doesn't really personify meatloaf, right? It gives you a good idea of what's going on, but it leaves a lot to the imagination. Those of you in geology are aware that minerals come into groups or categories. You, in lab, are responsible for learning the groups. We're going to acknowledge those groups in here. We're going to go really in depth into one of them in particular. But again, loosely speaking, generally speaking, there's two kinds of groups. We see the groups that are made up of compounds, which are the majority of them. And then we see minerals that are just composed of a single ingredient. Gold, silver, stuff like that. Copper. They are minerals, but they're also just, straight up elements. Whereas something like halite, salt, is sodium and chlorine. It's a compound, so on and so forth. So, just laying some groundwork here. So luckily for you guys, out of all those elements that make up the periodic table, you don't really have to learn a whole lot of them, thank goodness. There's really only 8 that show up over and over and over again. And I don't even hold you necessarily responsible for those 8. You will get used to them. You'll see them. Those top 2, though, out of that 8, yeah, you're going to want to know. All right? Because they're the big guys. That's the flour and sugar of baking right there, that oxygen and silicon. Okay? Those 2 ingredients account for 3/4 of the composition of the crust. Oxygen, again, we're going to round. Oxygen comes in at 47%, and silicon at 28%. There's your 75, right? So a lot of folks find that odd, and you will see questions, the primary component of the atmosphere, and everyone wants to think it's oxygen. I'd like to say at this point that we've told you nitrogen enough times that you remember it's not oxygen, but every so often somebody messes that one up. But then when we ask you what the primary component in the Earth is, well, oxygen, that gas, doesn't really come to mind, right? But lo and behold, it is the primary ingredient in the Earth's crust. So, anywho, behind oxygen and silicon, we've got aluminum, we've got iron, calcium, sodium, potassium, magnesium. And as you're going through those formulas, if you're doing the mineral lab, like we are in geology here, you see those ingredients a lot. You also see a handful of other stuff, don't get me wrong. That's because we're sort of cherry-picking the elements, so you see a little bit, the minerals. Cherry-picking through the minerals, so you see a little bit of everything. Okay. But yeah, those show up a lot, and there's good reason for that. Now, one of the lab groups has done mineral groups already. All right. And they can tell you, those of you that had lab yesterday, what mineral group did you write down more times than any of the others? Silicates, yeah. All right. The silicate mineral group is made out of, guess what? Silicon and oxygen. So when we see these numbers, it really goes to say, oh my gosh, I see why the silicates are the most common thing out there, because that's, geez, oh Pete's, nearly half of the Earth's crust is oxygen. Now again, not the gas, it's bonded to stuff, right? It's in compound form. But nonetheless, tons of oxygen in there. And then silicon comes in, a big jump above aluminum, all right? And again, I'm sure there's some chemistry stuff going on in the background. They love to bond together. They're just right for each other, so on and so forth. You know how chemistry is with their charges and their holes in their shells that they can patch together and whatnot. So don't worry about these percentages, again, except for the first two. Just more ranting about oxygen and silicon here. They make up nearly 3/4 of the composition of the Earth's crust, and they form the most common mineral group as well, the silicates. We just told you all of that. Okay, so this is just narrative. Don't scribble it down. And this is, again, what I mentioned a couple minutes ago. While we say that a mineral is composed of one or more elements, that is not the definition. It is a very specific definition. And for you folks at home, I will be looking for this definition, not the definition that Google gives you when you type it into your phone or whatever device you use. Okay? Please use this definition if you want your 4 points. So a mineral is 4 things, and we're going to talk about each of these 4 things. So if I do change slides before you get a chance to write them all down, don't fret. You will see each of them again as a topic heading. A mineral is naturally occurring. A mineral is inorganic. A mineral is crystalline. And a mineral is composed of a fixed, and that's fixed as in unchanging, set of chemical and physical properties. Now, as I've said 4 times already, I do want you to know this for the test. This is one of the exceptions for when you actually write something down. If you wish to do it as bullets like this, that's perfectly fine by me. I just need to see those, well, it's not 4 words, but those 4 concepts. It also blends rather nicely as a definition, sentence form, I should say. Naturally occurring inorganic substance with a crystalline structure and a fixed set of chemical and physical properties. Whichever works best for you, that's the one I suggest that you remember. So what do these guys mean? Naturally occurring. Well, it occurs naturally in nature. Not really helpful there, sorry. But it's not man-made, woman-made, squirrel-made. It just is. Naturally occurring. Every so often we get into conversations about synthetic gemstones at this point, and you know, that is sort of beauty's in the eye of the beholder kind of an answer. Obviously, if you're lab creating a sapphire or a diamond, that is no longer naturally occurring. We're sort of replicating. I suppose in a geologist's mind, it's along the lines of if you were cloning, you know, humans or sheep or whatever. That is no longer naturally occurring. But they are really nice. Inorganic. This one might seem contradictory coming right after naturally occurring. You're like, well, isn't everything that occurs organic? And no, not at all. All right. The prefix in means not, just a reminder. Insufficient, insubordinate, so on and so forth. So it is inorganic in the sense that it is not alive. It was never alive. It is not a byproduct of life. And that's one of the big differences that we see when we jump from minerals to rocks. Some rocks are organic. Coal is a great example. Coal was a marsh or a swamp in its previous life. There's some really cool rock we're going to look at that's made out of seashells, and so on and so forth. So some rocks are organic, but minerals, no. And at some point, you're also going to hear that, no, that's about rocks. I won't mention that. But, so yeah, minerals are inorganic, okay? Now, that's not saying that there aren't minerals in living things. I was going to talk to you about calcite and seashells, for example, just a moment ago. I stopped myself. Apparently, I'm going to talk to you a little bit about it. That calcite might be in a seashell, and that seashell was produced by a snail or a clam or whatever. All right. But that does not make the calcite organic. Crystalline. Well, there's a bit of difference here between, let's say you're looking at a hunk of crystal quartz. All right, everyone can picture that. Or a nice, pretty diamond. And say, oh, yes, crystals. I know what crystals are. Well, crystals are just about any geometric, three-dimensional geometric shape you could think of, and then some. Those are crystals, okay? And all solids are made of crystals. So in saying this, we're really just defining it as a solid structure. But we want to use, in this context, in this case, we want to use this term crystalline. Even if you can't see it, nice, pretty shapes to it, okay? The facets, as they say in the jewelry business. There are little crystals in there. And if, God forbid, this were an entire semester on minerals, okay, the class is called mineralogy. I've had it. Not my cup of tea, believe me. You would hear on and on and on about crystallography and all the angles of intersection, and goodness gracious, it's unbelievable what's out there. Okay, imagine this giant box of Legos just dumped upside down, and every conceivable building block piece, okay, is in there. There's a huge amount of diversity. Now, because crystallinity is so important, we're going to acknowledge it later on in this lecture. But we're going to just look at one crystal to show you how stuff works. But we're going to talk about it in the context of the silicate family. All right. Again, the most commonly occurring crystal that's out there. So we're honoring its heritage, its importance, but we're definitely going to limit it as well. And then last but not least, fixed properties. Again, we had a little conversation in lab yesterday. When we get close to the mineral practical, people start to get a little nervous and stuff. We're talking about how you guys are going to identify these things, without your scratch kits, without your charts, and so on and so forth. And I reiterated to them that, the properties remain the same. There was a method to the madness. There was a reason we sat there and had you do all those scratchings, all those, let's see if it has cleavage, let's see this, that, and the other thing. Because whether it's as big as a house or as big as a mouse, a piece of halite is always going to be cubic and clearish to whitish and not incredibly hard and taste salty, and it's because of that we could make those tables. And it's because of that those tables could be used by 20-year-olds that don't effectively know anything about this whatsoever, but still manage to get through the lab. All right, so if this weren't true, if this slide weren't true, none of that could be. Some of you wishing perhaps it wasn't, that's fine. But so the chemistry remains unchanged, and because the chemistry is unchanged, the physical manifestations, the properties, remain constant as well. Yes, there's some inherent variation, and this is, I think, what you guys struggle with more so than anything else. The fact that salt can sometimes look a little blue or gray. The fact that quartz comes in 6 colors. Yeah, I get it. It's annoying. All right, but that is tiny little imperfections. That's like you go over to a friend's house and say, oh my God, these chocolate chip cookies are so good. What did you do different? They're obviously chocolate chip cookies. You know that. But they taste just a little different than anything you've ever had. Oh, I just put a touch of cinnamon in. Oh, I just put a little. It doesn't change the makeup, the basic makeup of that cookie. It just, makes it a little unique. So that's more so what you guys deal with, what you struggle with, are those little uniquenesses. That was meant to be comforting, but I don't know if it was or if it wasn't. But the intent was supposed to be. So these properties remain constant, okay? And it's, again, because of all of that we can do this in the first place. So again, naturally occurring, inorganic, I guess I have another slide on fixed properties. Naturally occurring, inorganic, crystalline, and a fixed or unchanging set of chemical and then, therefore, physical properties. This slide, again, it's mostly narrative, but I used to say I don't care which you guys write first. If you write physical and chemical, chemical and physical, and I won't mark it wrong if you put physical first. But the purpose of this slide is to point out that it really is the chemistry underlying it all. Every so often when all of us science dorks get together for a meeting, we argue over, whose science is most important. Geology, I don't want to say we always lose, depends what you're measuring, but we're all the sciences, okay? Geology has everything in it, or science as well in general, just has every science in it. We're not just one. But if you really want to get down and dirty about it, chemistry, is what makes the physical world. And then the physicists will jump in and say, well, if it wasn't for physics, those chemicals wouldn't, okay, and it's a never-ending argument. But the chemical makes the physical, okay? That's what I wanted to stress here. And then again, it's back to those dang formulas, okay? All right. So classifying minerals. And this is where the importance in geology versus earth science starts to waver a little bit. Geology, it plays a much bigger picture. Earth science folks definitely don't tune out, though. Okay. In this class, we recognize 6 main groups of minerals. Out there in the world, you're going to see a handful of others. We'll talk about those a little later. In here, Just the one. Well, I'm sorry, just these ones. So the silicates, mentioned those already. The carbonates, the elementals, the halides or halides, it's up to you. The sulfurs and the oxides. Now again, for the half of this class that has had lab already, you know about your mineral groups. For the half that's going to wait till Monday, you'll get to hear this again. So it'll be a reminder then. You're going to see each of these again, so I'm switching here, but I'll give you 10, 9, 8, 7, a few more seconds here before I switch slides. Okay. Oops. So these silicates, the most common, boy, haven't you heard that a lot already? The most common mineral group at the surface of the earth must be important. We keep saying it. They consist of minerals made with the compound silica, SiO2. I don't have a question that makes you split these up. I'm sorry, SiO4. I don't have a question that makes you split these up, but one of the things you guys tend to trip up on are the three sort of conjugations of the silic word. You got silicon, that is the element. You got silica, that is the compound. And you've got silicates, which is the group. Silicon, silica, silicates. Got it? But again, I don't have some horrible question that makes you sort that out. But I will correct you when you swap one for the other orally. But try not to do it on paper. The carbonates. Again, we're looking at a compound. CO3. CO3 is the wonderful compound. It's carbon and 3 oxygens, of course. So we look for mineral formulas that have those ingredients in them. And we throw it then under the umbrella of carbonates. Now, we've been ranting and raving about how silicates are the most common and so on and so forth. Yeah, that's true, but oh my goodness, carbonates are absolutely everywhere. Carbonates are what limestone is made out of. And you may or may not recognize limestone at this point in your life. Soon you will. And then you will come to realize that limestone is absolutely everywhere as well. Limestone is anywhere that an ocean has been. Limestone only grows in oceans. And oceans have been just about everywhere at this point in the Earth's history. Here, obviously, too. You know, it doesn't take you long to figure out you've got seashell fossils and, gee, I wonder what that meant, you know. So you've kind of picked up on that through your years of life as well. You don't get seashell fossils without water. But sometimes limestone is not, you know, fossiliferous, so it's not always that evident. The problem with the carbonates is that they're not horribly diverse. You had, you know, a dozen plus silicate minerals, but you only had one carbonate in lab. Well, there's more. All right. But they're just, we just don't encounter them in lab. They don't look a whole heck of a lot different from one another. So the carbonates. The elementals, we've talked about already. Probably going to overshoot here. Yep, overshot again. The elementals are a mineral group for minerals that are composed only of a single ingredient. And there's a lot of them. Again, you see 3 or 4 of them in lab. You could think of a couple more yourself, perhaps. But there are, you know, even more of them. And it's the age-old joke, you know, what's the difference between copper, the element, and copper, the mineral? And I half-jokingly say, you know, how big it is. There really isn't a huge distinction there. It's really the context in which you're using it. Similarly, we're going to see rock salt as a sedimentary rock. And you guys asked me, what's the difference between rock salt and halite, the mineral that we saw. That one, it's a little easier because rock salt is sort of like the Marlboro Man of the mineral world there. It's just a big hunk and all beat up and grubby looking and just totally different than that pretty little crystal that we see in lab class for minerals. Now, because of a couple slides ago, right, if we were to whack that hunk of rock salt with a hammer and get a fresh, clean piece of it, it dang well better be a nice, pretty crystalline cube, okay? But rock salt as it stands looks a good bit different because it's been out there in the environment all weathered and whatnot. So a little foreshadowing just to try to alleviate some confusion you guys sometimes have in there. The halides. Even if you think you know the periodic table, very few of you know what the columns are named, vertical columns. Everyone knows the noble gases, right, all the way over to the right, and they had some really cool properties, and that's why they're oh so noble. But the column just before that is the halides, all right? And basically it has a whole bunch of stuff that ends in ene, I-N-E. You got bromine, chlorine, fluorine, iodine, all those guys. And what this boils down to is typically you guys have sorted through at the end of lab, you go through and you have to assign mineral groups to all the minerals you've looked at, and boy, you just can't figure one of them out. And somebody usually says, oh, hey, that's that one that he said. How about if we look, there's one group that we have to look at the periodic table for. Maybe this is that one. And you'll see that there's chlorine in the formula or fluoride in the formula. Fluorine, I should say, sorry. Fluorine in the formula. We don't have anything with bromine in it, but. So, at any rate, the halides. Kind of limited, but you've got a few. All right. As much as I grumble about artificial groupings, or will grumble about artificial groupings, there is one that we use. And it is for your benefit. That is the sulfur group. All right. If, again, this were mineralogy class, or even if this were at a four-year institution where I had a good chunk of geology majors, we would have 7 mineral groups. We would have the sulfates and the sulfites instead of just sulfur group. What it boils down to is how many oxygens are attached, and I even forget. One of them has 3, the other has 4, or one of them has 2, and one of them has 3. At any rate, and again, to those concerned with such things, that's important. For our purposes, not necessarily so important. So we lump anything that has the element sulfur in it, regardless of how many oxygens are next to it. We lump everything into the sulfur group. With one exception. Sulfur. Sulfur goes into the elementals because it is much more important that the sulfur exists just by itself than the fact that it happens to be sulfur, if that makes sense. So sort of when in doubt, elemental trumps all, okay? It's fairly unique that it's able to stand on its own like that. Last but not least, the oxides. This is another tough one. In lab, we just kind of give you a cheater on it and tell you which ones are the oxides. Oxidation obviously refers to the process wherein oxygen is added into the makeup of something that's existing. It oxidized, right? Usually we think about rust and how iron can oxidize. Well, lots of things oxidize. Tarnish is another word for oxidation, not just rust. Think about all the things out there that tarnish. right? If your grandmother has a silver tea set or something like that, every so often you see that it gets that black sort of sheen to it. Statue of Liberty, right? It's supposed to be made out of copper, but she's green. Why? Well, copper oxidizes or tarnishes in that manner, and so on and so forth. The problem comes in on your end when you're just looking at the formulas. It's tough for you to tell whether or not that oxygen was added because of exposure to the atmosphere, okay, or if that oxygen had always been there since the first day. There's some goofballs out there who are trying to argue that many of your silicates, quartz for example, is really nothing more than oxidized silicon. Okay, yeah, there is only silicon and oxygen in there. I get it. But I don't think they've won that argument with the mineralogists. I mean, because arguably, iron oxide is just iron and two oxygens. So if one does it, why not the other? Again, that's above my pay grade, right? As they say. And I'm going to let the mineralogists sort that out. But for the time being, if you think you see some glaring exception to these general rules I'm telling you about, feel free to ask me about it, or feel free just to accept them. This is just stuff that is told to us minor gods, and we pass it along, right? What else can we do? So we'll tell you that basically the rusty minerals in your box of rocks there are the ones that are the oxides. Okay. All right. Now, I mentioned artificial groupings once or twice, and this used to happen a lot more so before you guys as a demographic got so good at Google and stuff. Those folks that were really, concerned about doing well on the mineral and rock test would run out to Barnes & Nobles and buy a book. All right, My First Guide to Rocks and Minerals or whatever. Some sort of guide, field guide they used to call them. And in there, and even in your textbook, don't get me wrong, you're going to see references to things like gemstones and ores. And more so in the trade stuff, the stuff you get at a bookshop. But they're not wrong, they're just a little vague in general. Gemstones, for example, is used, anything that is shiny and pretty and has some sort of intrinsic value, whether it be in the eye of the beholder or just, its rareness. Not really horribly useful. Our groups are based on the chemistry, the most fundamental aspect, most fundamental component, okay? Not their use in the real world. I don't want to say that's irrelevant, but it's, if not secondary, it's tertiary even. Ores is another one. Ores are things that are dug up, right? Well, what do we dig up? We dig up iron, we dig up gold, we actually mine salt. I don't know if you guys know that. Living so close to Syracuse, hopefully you know that. It's Salt City. Toledo, where I used to live, actually has huge, in Cleveland. We see it a lot around the Great Lakes, has huge salt deposits, salt mines. There's three groups right there. Salt is in the halides. What do we say? Gold, right? Gold's an elemental. And iron is an oxide. So, yeah, you can have this lumping of ores, but it doesn't really tell you a whole lot about it. So, anyhow, point being, if you're out there on the internet and you're studying for this class, whether it be the mineral practical or the lecture practical, you're going to come across some other mineral groups out there. Please politely ignore them, okay? And stay with this half a dozen that we've given you in here. The one exception, of course, being sulfurs, which is done for your benefit. All right. So, as I said, we're going to go into depth with one of the groups. And that group is silica. We've told you at least 7 times now that it is the most commonly occurring mineral group at the surface of the earth. We've told you that it's made up of silicon and oxygen. we're going to now go more in depth into that part. It is, in fact, SiO4, okay? So SiO4 tells us that there are how many silicons? SiO4, one silicon, and how many oxygens? 4. There's the 4. All right. And they're arranged in a shape called a tetrahedron. Now, I'm going to keep calling this a pyramid for a little while because y'all can picture a pyramid a lot better than most of you can picture a tetrahedron. You know what a tetrahedron is? God bless. It's great. Okay. But a pyramid, most people could process and draw that. So, there she be. I've been teaching, I've been here 22 years, and I taught 3 or 4, maybe 5 years before that, and I don't know, it's probably because they chose to make these blue that it makes me think of racquetballs. And I've been saying, boy, I really ought to just glue 3 racquetballs together, and I could demonstrate this right in front of you. It's super. I've been thinking that for 25 years. You'd think I could glue 3 racquetballs together. I've been meaning to do that longer than most of you have been alive. I haven't done it yet. Now, if I were to set those 3 racquetballs together, you can picture pool balls if you don't know what a racquetball looks like. We'd make a little triangle on top of your desk, right? Then, in order to, what's that pink ball there representing? Well, what are the blue balls, first of all? Oxygen. So the blue balls are the oxygen. So what's the pink one? The silicon, okay? So anyhow, we got our 3 pool balls or our 3 racquetballs down on your table there. That's making the base of this here pyramid. Then we're going to take one of those super balls. Remember, you used to beg your parents to get you one of those bouncy balls out of the coin machine. All right. When I was a kid, there were 2 sizes. There was like the dime ones, which were the little guys, and then there were those big honking ones. By the time my kids were around, pretty much the only place you could find them was like Old Navy, and they just had the big ones in there. But I'm talking about those little tiny Super Ball things. Okay. So we're going to take one of those and we're going to set it on top of those pool balls. And then we're going to take another ball and put it on top of this little stack that we've made. Now, of course, in the real world, that would roll away. That would fall apart. We can't do it. And that's why I want to glue 3 racquetballs together. But mentally, if you could, picture that concept. So we got 3 on the bottom. We got that little tiny super ball in the middle. And then, boom, we're going to put a cap on top of that with 1 more ball. That is 4 large balls, your oxygen, and 1 small ball, your silicon. And arguably in a pyramidal shape on your desk. You dig? All right? And that is because of gravity. In the micro world that we're dealing with here, it is more this tetrahedron. So we've got 2 balls left to right there. And then the 2 balls on top are supposed to be front to back. So 1 coming towards you guys, 1 going back into the screen. Imagine if you could take your debit card and twist it. All right, so the corners are opposing one another. With your thumb and your pointer finger on the bottom 2 corners, your thumb and your pointer finger on the top 2 corners, and you could twist it. Again, you can't because it'd snap. But you could approximate twisting it. That's what the tetrahedron looks like. Okay? No problem with that operating in the tiny little world where we're doing this. But even here, you can imagine if this picture on the board were exposed to gravity, it would fall forwards or fall backwards. And again, you'd have the 3 balls on the ground, 1 on top. We're back to pyramid. Hence, me saying pyramid. You follow? Okay. Cool beans. Silicon oxygen tetrahedron is what this is called. That is the crystal shape. Tetrahedron is the crystal shape. This is the crystal. Silicon oxygen tetrahedron. Oh my gosh, the most common mineral group is the surface of the earth. Really? All right. So there's many types of silicates out there, made of many different elements. One thing that they all have in common is silica. And again, in lab, If you don't know this already, you will see it very, very soon. Hey, guess what bonds most commonly with silica? The remaining 6 elements. Don't bother rewriting this list. Never going to ask you. Just kind of making a point. Remember we had top 8 elements a couple minutes ago. We took out the top 2. Guess what bonds most frequently with them? The remaining 6. Now, when I first wrote this lecture, I went, of course, and looked at the stuff we see in lab. And you really don't see this stuff a whole lot, all right? But again, I've come to accept that that's really because we are cherry picking, so you see a little bit out of each of the groups and so on and so forth. But certainly in your feldspars and some of your other silicates, you will see these elements show up. Okay, yet again, repetition. So there are 4 main ways that these silicates can be arranged. And again, not to keep referring to a lab that half of you haven't done yet, I do apologize for that. But once you see, and I think yesterday's folks will agree with me, once you see how many different minerals are silicates, and they really don't look anything like each other, with very few exceptions. All the feldspars look like feldspars. Yes, okay. But the feldspars don't look like micas by any means. The hornblende doesn't look like quartz, and so on. There's variation, okay? And that's because we take those little tetrahedra and we can arrange them in a couple of different ways. So we're going to now, briefly, I'm going to kind of go fast through this because we're running out of time, but I do want to address it. All right. So isolated, chain, sheet, and framework. Isolated makes more sense in retrospect. So when I talk about isolated now, just sort of smile and nod. We will, again, once we get a little further in, you'll be like, oh, okay, that's what he meant. So it's a single tetrahedra that's bonded to other tetrahedra. It's not just that there's one. Okay, that's not how it's isolated. That hunk of olivine, okay, which is a great example of what's going on here, isn't one tetrahedra. It's made up of thousands, let's just say. But what's important is that those tetrahedra aren't really bonded to each other. That's how they're isolated. They don't share any chemical bonds with the others. Which is why, okay, the hardness test on olivine failed so miserably. Heck, you don't even have to drag a steel nail across olivine to get a handful of green sand. You can just rub it with your thumb and it falls apart. Okay, those tetrahedra are held together by a little more than static electricity. It's not static electricity. Please don't repeat that. But it's a similar, something you're familiar with. You rub a balloon on your sweater and it sticks to your hair kind of thing. Okay? It's a similar force. So some olivine, some garnet. Next comes the chain silicates. And now you'll see, the variance here. With the chain structure, these tetrahedra actually share a bond. Or 2, depending. So now they're sort of daisy chained together like paper clips, right? Again, imagine these pyramids here. I should have pointed this out a minute ago, I suppose. What does, structurally speaking, what's at each corner of this pyramid? What does each corner represent? Oxygens, yeah, okay. Handful you had chemistry. Good. For the rest of you that haven't, this is just it's similar to the ball and stick idea, okay, that you see a lot in chemistry. So each corner here is an oxygen. That silicon is tucked down in the center. You can't really see it. So oxygen to oxygen, those are great bonds. Those are really strong bonds, okay? So we see then in our chain silicates that you've got at least, we've got single chain and double chain. Okay, you're sharing at least one oxygen bond there with another tetrahedron. We move to a double chain. Well, you're using up even more of your oxygens for bonding. Specimen 9 and specimen 10, your hornblende and your augite. Again, remember on paper they were really seemingly identical in a lot of their properties. They mentioned cleavage, and well, if we could mention this, it would be almost even more helpful. I had to give you the little cheaters that one of them looked like long black toothpicks, and the other was kind of just really grainy, but it also had some greenish tint to it. Well, this double chain and single chain is why I think, again, I'm not a mineralogist, but why I think we can see the hornblende, those toothpicks, because they're twice as wide. All right, they're just that much bigger that it stands out more so in the makeup of the specimen. Now, again, I could be completely wrong, but that makes sense to me. So we've got augite in the upper left-hand corner, I think, and because it's greenish tint to it, right? And we've got our hornblende in the bottom right, and you can see, hopefully, the layering in there. Next, we've got our sheet silicates. The sheet silicates are basically 3 or more chains. Okay, technically a lot more. But we just move up beyond double chain, and we start forming these sheets. What comes to mind when we talk about sheets? The micas, yeah, exactly. Okay, and this illustrates something else really cool about the micas. You could flake those apart, sheet by sheet by sheet. But I don't know if any of you did this. Sometimes just fidgeting, you'll do it. You get one individual sheet. You could put it in between your fingers and bend that sucker practically together, and it won't crack in half. Very elastic. Okay, and again, that's pointing to those oxygen bonds in there that are just super strong, okay? But together, top to bottom, it's just like that olivine. It's nothing more than something resembling static electricity holding it together. And that's what's coming in the last. That, and also your talc, by the way. Your talc too. But talc's hard to flake apart, but the mica's for sure. But that's what's coming here in these frameworks. The last one is that top to bottom bond. All right. We take that last remaining oxygen, the top of that pyramid, and we bond it to the bottom of the pyramid above it. So now not only do you have that strength across it, but you've got it up and down. And your textbook will mention some accessory elements or ions. I forget what word they even use. There's a little more going on. I'm simplifying it a bit, okay? But just picture the top of that pyramid gluing to the bottom of the pyramid above it, tetrahedron to tetrahedron, of course. And that's where we're at with these guys. These are your quartzes. These are your feldspars, which incidentally were some of your strongest. Arguably, hornblende and augite are just as hard, but some of your strongest, hardest minerals out there. And we told you that silicates comprise nearly 3/4 of the Earth's crust. Well, nearly 3/4 of those are these guys, your quartzes and your feldspars. And again, it just goes to reason, in my mind, that, yeah, those micas, after 4.5 billion years, those micas are going to break down, wear away, flake out. The olivine's going to, break down. You see these things that just aren't as durable kind of fade out of the equation, whereas these other guys tend to stick around. And again, I'm sure I'm oversimplifying it even in my brain, but But you will see when we move on to igneous rocks, you're going to see quartzes and feldspars over and over and over again. Yeah, there'll be some micas here and there and some other stuff, but these are the big guys. And again, it probably boils down to really nothing more than elemental composition. But so again, isolated, chain, sheet, and framework. Please, in the back of your head, attach an example to each of these. There is a question about that on the test, okay? Which of these is an example of isolated? Which of these is an example of chain? So on and so forth. So it's here in the PowerPoints. If you're tired and you didn't write stuff down right now, get yourself a copy of those and pay attention to it. Now, believe it or not, that's all we're going to do about minerals. Again, the earth science folks are like, yay, we're done with minerals. But you guys on the geology side of things, you're like, wait a minute, we just spent 3 stinking weeks on this in lab, and you're going to give us 50 minutes of it in lecture? Yeah. That's because minerals is best taught with them in your hand, okay, and we kind of just reinforced a lot of what we did in the lab room. For a class where, geology is just one aspect of the entire semester, like earth sciences, we focus, a lot less on it. So, now you guys are probably wishing you'd taken earth science, right? But, so at any rate, much like the rocks, okay, it's you learn a lot more when they're actually in front of you in your hands, and you can poke them, scratch them, sniff them, lick them, whatever you got to do. So read the minerals chapter. For many of you, this is the first time we actually have a lecture that lines up with a chapter, for goodness sakes. Okay? So read the minerals chapter. You see stuff in there that we didn't talk about. Okay, that's fine. If you have questions, ask me about it. I'm not going to test you on stuff we did not cover in lecture. So if you see something in the book that we didn't talk about, don't get too stressy about it. But as I said, if you have questions, you can ask. Similarly, if I talk about something in here that really wasn't in the book so much, but I went into it a whole lot, well, assume that I'm going to test to that level as well. All right? So the book is a good background. It's a good reference. But lecture is a guide to what's important for the test. So, all right, you guys. Thank you for your patience.